I promise I'm not going to shake the camera around this time. So let's go through how to solve this. Here we go. So you've got a weight force on the 3 kilogram here. I'm going to try that, draw that straight. Hey, better. On that 3 kilogram, you also have a tension going upwards. You have a tension going forward. You have a normal force. And you have a weight force. Notice that the hanging one doesn't have a weight, a normal force. I see it a lot of times where students will draw a normal force on the weight. Normal force means you have a surface pushing. So now let's go through and let's cross off our forces that are canceling each other out. So the one that's on the surface, remember this is an air track like the last problem, the weight and the normal cancel each other out. Remember what we did with the tug of war, Newton's third law. The two tensions cancel out. The only thing that's not canceled out is this weight force. So this is your net force that's going to drive your system. So let's set it up. We got F net equals MA, not for the individual, but for the system. So the net force for the system is the weight of the hanging mass. And then the mass that gets accelerated is both of them. So the hanging weights, well, if he's 3 kilograms, his weight force is mg, which is 3 times 9.8. Because the problem I use 9.8, so 3 times 9.8, I get 29.4. Okay, so I get 29.4 newtons. The mass involved is I have 3 kilograms up top, up here, and I have 3 kilograms down here. So together, both of those masses are being accelerated. So I've got 29.4 equals 6 times A. So the acceleration is 29.4 divided by 6, 4.9 meters per second squared. Way to think about that is if that thing up top wasn't there, it'd be accelerating at 9.8 meters per second squared. But since the thing up top is the same mass, you've doubled the mass. Well, if you double the mass with the same force, you half the acceleration. So I hope this helps a little bit.